All right. Hello. Good morning. Good afternoon. Good evening. Good night, wherever you are in the world. And again, welcome to the stream. Okay, let me just put my lab coat on. Yeah, the lab coat's an essential part of the lesson. Now, it actually helps with the green screen too. So I need to put it on just to help with the green screen. See, big difference. Without the coat, with the coat. So yeah, the coat really helps. It's not just for uh, it's not just for it's not just a get up. It's really part of the thing. Okay, so today we're gonna do a lesson with CJ. He's not in yet. I think I better send him a message. All right. Ah, hold on. I do have a message. Hold on. Yeah, apparently he's already inside. So, hmm. So there's this glitch apparently. Sometimes it happens. It's like sometimes he's in, but it doesn't register that he's in, and also sometimes I'm in, it doesn't register to him that I'm in. So it's like we're waiting for each other for something. So hold on. Uh, hmm. Yep, he's in, but I'll just wait for him to get back in. Alright. Yeah, I think it's glitching. Let's do a paper one question first. The four paper one should be enough. Hmm. Alright, so he's also in the lesson, but he cannot see me. So what I'll do, I'll just call him. CJ, if you're on the stream, let's meet through. Well, what was the last time? What was the last thing we used? Was it Zoom or Google Meet? Either way. Okay, so hmm. Oh, okay. I'm gonna uh what's this? Refresh my browser for a while. Ah, there it is. There we go. The
Yeah.
refresh worked. Oh,
Did you refresh your browser?
yeah.
Mr. Dennis, what?
Can you hear me?
I'm opening my tab. Yes, hello.
All right.
I've been
Okay.
opening my tab over and over.
Well, good. Well, that was really good news. You got a six on paper too.
Oh, the paper one.
Yeah, but your paper one, we kind of need to work on it, I guess. Uh, you have the questions?
Oh, no.
Oh, it's
I'm on
fine.
my break now.
Oh, you're on a break.
Yes.
Okay. All right. So this is what we'll do. I have here a couple of past paper questions. We'll go. What we'll do is we're gonna basically do some questions first about topic 8. Okay, specifically the energy production bit, not the global warming bit just yet. All right. Okay. So, ready?
Okay.
All right. So here's the first question. Oh, by the way, before that, Jamboard link. I'll just share that with you as well. Okay. There we go. So it's shared and you should be able to access it. And of course, as usual, it's being streamed. So you can check out the lesson later if you need to. Okay. So
Mhm.
anyway, here's the first question. Hey, it's not pasting. Let's do that again. Okay, so first question is, you remember the thing I said about solar panels? That usually it's about areas and you just need to calculate certain values from that. Well, here's an example of that. Okay, so you have a surface area given and an efficiency given at 50%.
What's the
Okay.
dice not streaming?
Oh, hold on. Let me share the screen. There we go. Hmm. All right, so you have the average intensity is also given as 0.25 kilowatts per square meter. What's the average power output from an array of 10 of those panels? This one's pretty straightforward, I think, if you know what to do with the numbers.
Hmm. Is there any equation?
No. Now, if there is no equation for solar panels, so what do you need to do? You just have to make sure your units end up being just watts or kilowatts, right? So I think you can start with
Yes.
watts. So how can you cancel out every other unit there? That's usually the
Cancel? Oh,
that's what you need to do. You need to cancel out all the units that are not watts there, and then you have to figure out where to put the efficiency, where you put those 10 solar panels in there. Okay.
so get rid of the meters.
So how do you do that?
Um, well, the m
Mm-hmm.
inverse squared is
Mm-hmm.
like probably cancels out with the m squared.
Right. It does. Correct.
So then it's like 0.4 and then 0.25 kW.
Mm-hmm.
But we want to change that to W, so it's 10 to the power of 3. So
Correct.
it's 250.
All right.
Wait, is it?
It is.
Yes, 250.
Mm-hmm.
And the efficiency is that 50%?
So okay, it's 50% correct.
50%.
So I'll just write down what
So is
you're
the
saying.
it's just
Carry on.
I'm thinking
So I'm just gonna write down what you just said. Then you're gonna
it's
multiply
50 watts.
50 watts. The answer is C. Okay. So this is
Mhm.
correct. Okay. I'm gonna give you
Okay.
another. I'm gonna give you another way to do this without calculation. But let's do the calculation first, right? So you're
Mhm.
right to do this. So 0.4 square meters. Then you multiply this by. We're gonna convert that to watts instead of kilowatts. So that's gonna be 250 watts per square meter. So these cancel out already, right? And then you're gonna have to
Mhm.
get the efficiency, 0.5, right? And then you're gonna multiply these by how many solar panels you have. Okay.
Mhm.
So what's gonna happen? So this is gonna give you this is gonna be 100 times 10 times half of it. Sorry, let's do that again. So Let's put that in the calculator just to be safe. Oh, but then again, this is no calculator, so you can't do calculator, right? So let's do 4
Mhm.
times 0.5 times 250. The answer is 500 watts. Okay,
Uh,
not 50. Not why 50 is correct for one panel. So this is for one panel,
oh, okay, that makes sense. Yes.
but you have 10 panels in the question, right?
Yeah.
Okay, so that's why it's gonna become 500 watts. Okay, so how am I gonna do this without actually fully solving it? I'm just gonna get rid of two answers already. I know that at 50%, a single panel is gonna give me 125, a square meter of the thing, right? So
Mhm.
that already gets rid of A and B. 125 is the minimum power output I can get, right? So
Yeah.
yeah, so C and D are still kind of okay because of the efficiencies and stuff and sizes, but A and B definitely wrong. Now from there we can say that it's D, okay, by calculation. So just be careful. You just have to read the text. You got the idea right, but you just
Mhm.
really forgot the fact that there are 10 panels. Okay, so be careful. All right, so the second problem is here. This is something you should know. Again, this is true for any kind of heat-based power generation. Heat-based power generation. So that's fossil, nuclear, and geothermal. The only thing that's different is the beginning. Where does it start? Okay. So anyway,
Mhm.
if it says here it's coal, right? So which
Is
would
it D?
no,
Then C. Wait. Um, A.
no, it's not A. Okay, I'll give you a clue. You start from coal. What do you do with coal?
You burn it.
You burn it. So what's the transformation that happens in
Um, chemical to burning, and then kinetic energy because the when you burn it, the
burning?
particles move faster,
Right.
and then
Okay,
you get
but
energy.
but when we said particles, we don't normally consider that kinetic, even though
Molecules. Oh,
it's in the form of molecules. So when we say that, it's not normally kinetic. We don't call it kinetic, even though at the at the very base of it, it is still kinetic. But generally speaking, when that happens, you call it thermal energy. It's about heat, right?
mhm.
Mm. So with that, what's the best answer? You said chemical to start with, so it's either B or C.
Is it C?
It's C, the correct answer. Okay. So again, I will just write it here for fossil fuel. So before that, this is always the last three steps. N- no question about it. Last three steps is kinetic. Sorry, it's not C. I misread that. It's B.
What?
It should be B. Oops. It's I misread that. I was reading. I wanted to say B, but somehow I switched kinetic and thermal. But anyway, it's the same thing. Okay. The correct answer is B. Okay, because these is are always the last three steps for any type of fuel, fuel based, nuclear, or geothermal. Okay, there are some solar types, some solar. Okay, but we don't really discuss this much, this particular form of solar. Okay, but the rest of solar we skip a few things, and then the other forms we don't go through these steps altogether. Okay, Now, for fossil fuels, it's gonna be chemical. Okay, so let's just put that here. This will always be chemical. Okay, nuclear will always, of course, be nuclear energy, and geothermal would be straight thermal. No, geothermal is first.
Hmm.
Okay, so again, fossil fuels starts with chemical, nuclear energy starts with nuclear energy, of course, and geothermal starts with thermal. But the rest are the
Hmm.
same. It's always in that order: thermal, kinetic, electric. Okay.
Okay.
All right. Great. Let's move on to the next few questions. This is from the next paper. Hmm. All right. Let's start with something easy first. Something you've already learned. So, which of these is not a primary energy source?
Right. Jet engine. Wait, no.
Think about it.
Yes? No. Doesn't jet like use fuel and then like boom, coal fire. Hmm. Coal chemical
Okay.
to
I'll give you a clue. I'll give you a clue. If you take the energy straight from the source, that's primary. If you take the energy and convert it to something else, it's not primary. You have to think of the energy about here. Okay.
you said straight from the source, so straight from the engine, so like straight from fuel.
Mm-hmm. Straight from the fuel, exactly. So if it's straight from the fuel, it's primary.
Yeah.
Okay. And I got a message on Twitch. I'll just read it for the stream, yeah. So how's it going? Loving the content. This is from Zigzag on the bag. Our content is similar, definitely not. All right, I'll follow you as well, Zigzag. Once I'm done with the lesson. Right, thank you. But anyway, going back. So definitely primary. So let's label this, right? How about the wind
Hmm.
turbine?
It uses wind and then changes it into electricity, no?
It kind of does, but do you take like other steps to get to electricity? Because if you think about this, let's take a look at the jet engine. This is chemical into kinetic, right? There's only one step. That's one way you can think of primary, one step conversion.
Hmm.
Okay. Secondary is two-step conversion. Okay. So which ones here is like one-step conversion?
That's a good question.
Mm-hmm.
Coal fire seems like one step. Is it not? You burn it and then
Mm-hmm.
it turns into oh, but you burn it and then it turns into like something.
Mm-hmm.
Nuclear is one step.
Nuclear is also one step. Okay.
Isn't coal primary?
Actually, coal is secondary. A lot of the time, coal-fired power stations are secondary. Wind turbines can be
Most of
primary
the time?
most of the time. We are trying to develop some technologies that would develop the kinetic energy straight into electricity.
Hmm.
Mm. So nuclear power station though, this can be primary or secondary. So the only one that's definitely secondary is C. Okay.
Okay.
What happens in wind turbines? This is wind, so kinetic energy straight into electric, right?
Hmm.
Okay. Coal-fired stations are definitely chemical first, into heat, and then into kinetic energy, then into electricity. So more than two steps, right? Nuclear power stations, um, some there are some nuclear power stations that harness the heat straight away. So nuclear to heat. So nuclear to heat. Actually, no. I'm a Now that I think about it, no. Nuclear power stations should also be secondary. Okay, in this case, I think I'll consult the mark scheme because in this case, it is not clear, right? Let me just check the mark scheme real quick. Which paper is this?
Is it
Uh,
nuclear power first, primary?
mm-hmm. Hold on, let me check. 16, mark scheme. Here we go. And what number is this? This is number 29. 29 is B. Oh, okay. Okay.
It
All
is
right.
B.
I don't know why, but it's jet engine in the mark scheme. Now, if you think about it, that's the odd one out, right?
Yeah.
Yeah. Uh, okay, this is really strange for me because the only reason jet engine is the answer here is because it's the odd one out. Okay. Uh, okay, I think I better get back to you later. I'll probably think about this first, why this is the answer. Because this is weird. This is weird for me. Because according to the definitions, this should be that should not be the answer. But anyway, let's do another one. That's weird. All right, this one should be a bit easy. We haven't done these yet, but I'm gonna put this here so we have something to refer to. Okay, so I'll teach you this, but I will not tell you the answer yet.
Okay.
All right. So what we have here is what's called a Sankey diagram. It's still
Sankey
loading.
die. Oh, the arrows thingy.
The arrows thingy. I think you've learned that before. Hold on, it's loading. All right, so there we go. So what? How do you determine how much energy goes in or out? Remember that in a Sankey diagram, what comes in, this is 100%. Okay, which you
Mm-hmm.
just represent by the number of squares on the width. So how many wide width in squares, right? And then the rest of it will basically be broken down into different parts. So in this case, let's count this now. How many small squares do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 squares here. Okay. So how much energy? Let's take a look here. How much energy or how many squares is lost in the power station? Or better yet, let's go to the question first. What's the overall efficiency of the power station? So how do
What?
you find efficiency?
Um, um, total work out
Uh-huh.
minus use
So
work in. Total work in.
out uh over in. Okay. Times 100%, of course, right?
Mm-hmm.
But we're gonna have to use a different
Yeah.
we're gonna have to use a word here. It's not total out, it's useful output. Okay?
Yeah, useful.
It's not total. Because if you just go for total, that's gonna be 100%, right?
Mm-hmm.
Useful out divided by this time total in. Okay, that's the efficiency. So where's the useful output here? Where's the useful output?
Is it where the arrows are?
Mm-hmm. Which arrow is it? Is it which one of these arrows?
It
Customers,
practically
transmission.
covers the top part of the question.
Ah, okay.
What is it?
Let
What's the
let me let me adjust that. Hold on. There we go.
um,
Hope you can read that.
yes. Hmm.
Let me just rewrite everything here. So this is 100%.
coal-fired power station.
Okay.
Do you count like every square, like just every other square
You don't count
that
the
isn't from
arrow.
the start?
Yeah, you have to count from the very beginning, but you do not count these ones, like the edges of the arrows. You
Hmm.
don't count those, so don't count that. Okay. Uh, okay. I'm gonna give you a question. Which one here? Which one of these four things is the useful output?
The useful output is where the the arrows are, but not the arrows.
But only one of those arrows is useful.
Is it the not the thermal energy loss?
Okay, definitely not this.
Energy to customers?
Energy to customers is correct. That's the useful output, right? So, how wide is that?
That's one. It's 3 blocks wide.
That's three boxes, right? Or three squares. So this is the thing about Sankey diagrams. You don't have to do this in terms of the actual units. You just have to count squares. So what's the efficiency?
So it's 30%? Oh,
30%.
30%.
It is 30%, but 30% would be which answer?
0.38.
0.3. So that's the answer. Okay. Um, okay, how much is used in transmission? This is 10%. In the power station, this is
Yes.
also 10%. And how much is lost? A whopping 50%.
Uh, yeah.
Okay. Actually, yeah, that's most of the energy that's lost in electricity generation is lost in the power station itself. It doesn't matter what kind of power station it is.
Yeah.
Most mhm.
Isn't like most of the coal burns in like factory or like whatever plants? Like, don't we only get 30% of that energy?
Approximately, and that's in the
Which is
station already,
unfortunate.
right? The most efficient
Yeah.
things we have, if I'm not
Nuclear?
mistaken, no, not even nuclear. The most efficient thing is either wind or solar.
Hmm.
If it's solar, we're now at around 40% efficiency. Not bad,
That's
but it's still we're
not
still
good.
yeah, we're still wasting more than half of the energy available. Yeah. That's and 40% is like the maximum. Typical values are still at 30% or 35%. Yeah, so that's the thing there. All right, moving on. Next question. Uh, what are the okay? This we haven't studied, but this is just a factual thing, so I'm gonna put this up. Okay. Now, solar power comes in two flavors for heating and photovoltaic. So I'll put it here. Okay, let me explain first. Well, I don't think we need to. I think this is a pretty easy answer.
What's photovoltaic
Okay,
cell?
I'll give you one clue to help you out. Oops, that's too wide.
Volt?
Volt. That's your clue.
Well, cut out thermal, I guess.
Mm-hmm. So what's the answer? Is it A, B, C, or D?
Um, A?
Correct. It's A. Okay. Now, excuse me. Uh, the idea here is that photovoltaic cells, these are now what we now normally call solar cells. Okay. Again, these are what we call solar cells. So,
I still don't know what solar cells are.
okay.
Sorry.
Okay, so let's just do it here. These are the ones that we normally call solar cells now. Okay. So basically,
Hmm.
these devices, photovoltaic cells, they convert light straight into electricity. So light into electricity.
Mm-hmm.
Okay. Now, a solar heating panel. This is basically a box with a glass top. Okay.
Mm-hmm.
And what do they do? They do the main thing they do is they collect heat from the sun.
Mm.
Okay. The heat is collected either through the infrared or through visible light. The visible light gets absorbed by the box and then it gets released back as infrared, turns makes it hotter inside. Okay, inside the box. I'm gonna show you a quick image of that solar heating panel. Um, it's actually quite a common thing to be seen in tropical countries, so you should see this there in uh, around you if you don't have one. There's a good picture of that. Ah, this one. Copy this. So this is a good example of a solar heating panel. Okay. While that's loading, the idea here is it's basically like I said, got a glass top and it's a box, and the box is painted black on the inside. Okay. Why is it taking so long to load? All right. So all right, we'll get back to that once the image loads. Okay. Hopefully within the next minute or so.
Mm-hmm.
All right. Let's go now to the next question. Okay, this one's done. That's also that. Okay, this we have one question here. This one's more. This one I think is a better way of putting the question for primary versus secondary source. So we have this. Following are energy sources. Which of these are secondary energy sources? Is it the battery of rechargeable electric cells? Is it crude oil, or is it a pumped storage hydroelectric system?
Mm. Okay. Is crude oil a secondary? Because you have to like refine it or something.
Well, kind of, but not really.
Really?
Okay, think about it this way: even if you have to refine it, the act of refining does not actually extract energy from it, right?
Yeah.
So the act of refining is not part of the energy extraction process. It makes it better eventually, but it's not really part of it. Or here's another way of thinking about it: in crude oil can be burned straight away. You don't have to refine it. It just makes it better if you do, right?
Okay.
Okay, so
Then cut out A and B. Cut out B. Battery of rechargeable. I think one is yes.
uh-huh. Well,
Oh no no no. One's primary. No.
okay, go back to what you said. You said cut out.
Wait what?
This is wrong. You said that's wrong, right? So you said cut out A.
Wait wait no. You said crude oil is primary.
Yeah, crude oil is primary. So the question's secondary, right?
Yeah
So let's cut out A, as you
yeah.
said. And then what else do you cut out? You have to cut out C, right?
Oh, C and D
C and D also have to be cut out. So the only answer left
is B.
is B. That's the correct answer there.
Okay.
All right. So the idea here is, okay, this is you're storing energy here, right? This is also storing energy. So another way of thinking about secondary is if you can store the energy. Um, Actually, yeah. In this case, it's they're stored from electricity, right? And what just happened? Okay. Stored from electricity, right? Okay. Now I
Mm-hmm.
think have you learned about pump storage hydroelectric systems yet?
No.
Oh, okay. I'll take a pump storage. I'll take an image, see if it loads relatively quick. Which one's a good image? This one. Okay. So just so we're clear, a pump storage energy system is basically just a hydroelectric power station. Okay, but the way that it's set up, the way that it's set up, it's actually got two. Uh, when you have a normal power station or a normal hydroelectric station, you have one reservoir, right? In pump storage systems, you have two, the upper and the lower. Okay, so what happens here is that when the water is up here, so when the water flows this way, flows down, it's a normal hydroelectric. In other words, this is normal mode going down, right? But there are times wherein electricity is cheap because it's not in high demand, right? So if you think about it, this kind of goes into economics, demand and supply, right? If there's a high supply but low demand, the prices will be low, right? And in this case, there's a lot of electricity but no one to use it, so the prices will be low in certain times. So when prices are low, electric prices are low, it acts in reverse. It goes in reverse. Okay.
If the
Uh,
what's low?
can you see that? Oh, I don't think you can see that. I'm gonna change colors. Okay. Or better yet, I think
Oh,
I better put that in its own screen. Hold on. Its own page. So this is again a pump storage hydroelectric system. It's basically this, right? So what happens again is in normal mode, water goes down. So water, right? And in this case, this is generating electricity. Generate electricity. Okay. Now on the other side, here, the flow of water is up. Okay. This is a pump mode. What happens in pump mode? The pumps are activated, so flow of water is up. Now this is done when electricity is cheap. Done when electricity is cheap. Okay. So in this
mm,
case, this uses electricity. So what's the key idea here? These stations make money because in whatever we do anyway, there's always part of it that's about profit, or at least making money, right? So this station makes money by
mm,
selling the electricity in normal mode at a higher price. And then when the price of the electricity is low, it pumps the water back up. Okay. When does this normally
okay.
happen? So when does this normally happen? Normal mode usually happens if a spike in demand is a spike in demand is present. Okay,
Mhm.
spike in demand. Okay. Now, when is pump mode used? Pump
Mhm.
mode is again used when demand is low.
Mhm.
Okay, there. So that is basically what a pump storage hydroelectric system is. Excuse me. All right, questions? Is that clear?
So like when the demand is low, it pumps. When the demand is high, it pulls.
Mm-hmm. So again, that's correct. So when the demand for electricity is low, it pumps the when the demand is low, electricity prices are low, right? So they use that to
Yeah.
pump the water up. But when the demand of electricity
Mhm.
is high, then prices for electricity. Okay, I think this is a bit of nuclear physics and a bit of knowing what nuclear power stations do.